Okay, you guys. So in this lecture, let me jump in and start introducing ring closing metathesis. And you really can't understand ring closing metathesis unless we do an example and we walk and talk you through it, or I walk and talk you through it. And so let me go ahead and do that. And as I'm going through the example, I'll go ahead and jot down the rules, because if I just write out the rules, it won't make a lot of sense. Okay. So example number one. Say these are two CH3 groups. We'll keep our alkenes simple, and I'll draw out my catalyst. And so what I'll do is I'll also number my substituents and my carbons so that you can see what's happening and what we're forming. Okay. So you can start to see that what we went over in part two of this lecture, we talked about when we closed the ring, we formed a pi system within the ring, and we also had to account for the tail end carbons that are on the skeleton chain and the fact that they form their own byproduct. And so we have to take into account all of that. Okay. Just like with our previous cross-coupling reactions, we always start with the metal catalyst, in this case, our ruthenium catalyst. It's going to get a little crowded. These catalytic cycles are much longer than what we're used to. So bear with me. They also don't follow similar steps to what we've learned before. And so what I mean is there's clearly no leaving group, right? There's no halogen to our starting material. So there's no oxidative addition. There's no reductive elimination. So it's slightly different steps than what we're used to. So we've introduced our catalyst as our first step. And if you remember, it's got 16 electrons, unsaturated. We introduce our starting material, and I'll go through this slowly, even if we get through one example in this last part, that's fine. Continue to number it. And step number one is known as ligand association, which is just one of the double bonds complexing to the ruthenium. Again, I'll continue to number it. I chose the double bond on the right. of my starting material. If you want to choose the double bond on the left, that's perfectly fine. Absolutely perfectly fine. I just chose this bond. We are now at 18 electrons. Nothing else can be added to this ruthenium, right? It's saturated. We started with a 16 electron system. So step number 2 is known as ligand dissociation. One of the ligands has to come off. And the ligand that always comes off is the phosphorus ligand. So the first 2 steps to Grubb's metathesis are always the same. Ligand association followed by ligand dissociation. The ligand that comes off is always a phosphine ligand, also a neutral ligand. Okay? So let's draw that product. And what I'm going to do now is I'm going to try to draw out my chain in a way that makes it easier for me to see. And I'll continue to number it. Okay. That's our product that results from ligand dissociation. The next step is a pseudo migratory insertion. Okay. And a pseudo migratory insertion looks as follows. Electrons attack the double bond at carbon 7. The pi bond attacks the ruthenium. And so what you're forming is a 4-membered ring. It's called a pseudo-migratory insertion because typically when we're doing a migratory insertion and you go back to your cross-coupling reactions, you're not forming a 4-membered ring. It's just one substituent moving over, and that's it. In this case, it's the 2 pi electrons, or excuse me, the 2 pi systems attacking each other to form a 4-membered ring. This is known as a metallocycle. It's a cyclic system that's made up of a metal, hence metallocycle. Okay. Once it does its pseudo-migratory insertion, it collapses. And it collapses because the 4-membered ring is strained. And not only is it strained, but now the ruthenium is part of the skeletal chain once it collapses. So if you follow your arrows, what you will see is the following. Let me continue to number this. Notice how carbon 6 is now double bonded to the ruthenium. Please also notice that carbon 6 and carbon 7 are no longer bonded, and the ruthenium and the carbon with the phenyl group are no longer bonded. And so my byproduct is carbon 7 bonded to the carbon and phenyl group. This is my byproduct. Okay, we're not done with it because every catalytic cycle, if you remember, you have to return to your catalyst. You have to regenerate your catalyst. And my catalyst has a phenyl group on it. So I'm going to have to use this byproduct eventually. Okay. So rule number 1 to this. Always add ruthenium during the pseudo migratory insertion step to the more substituted carbon. Notice how ruthenium was added to carbon 6, the more substituted carbon of the chain of your chain. The reason for that is that ruthenium is now part of your chain. And because now it's part of your chain, it can keep going and start reacting with the other double bond. Okay? So what you're trying to do in your first step is to include ruthenium as part of your chain so it can keep moving on. Okay, so that's rule number 1. And now that it's part of my chain, now it can react with the other double bond. So what I'll try to do, I'll try my best to do this, is to redraw this. This is just an equal sign to show you that I'm redrawing it so that the ruthenium and the double bond are right next to each other. So bear with me. Okay. Notice that nothing has changed. I still have my chain from 1 to 6. I still have my methyl groups at carbon 4. My ruthenium is still double bonded to carbon 6 in the form of a carbene. Excuse me. I'll add my substituents on here. The beauty of it is that now they're right next to each other. They're parallel to each other. Okay. Again, I do a pseudo-migratory insertion, just like I did before. Alkene or carbene attacks my alkene, attacks the ruthenium, just like before. Pseudo-migratory insertion. Pseudo insertion. Okay. Again, I am going to form a 4-membered ring. So follow your arrows. Notice, I'm going to draw the top first because that's probably the easiest. Notice that now there is a bond between 2 and 6. Notice that 2 is still bonded to 1. Carbon 6 is still bonded to the ruthenium, but ruthenium and carbon 1 are now bonded to each other. There's my 4-membered ring. Let me add on my substituents. Okay. This is rule number 2. Okay. Rule number 2 says once ruthenium is part of your chain, the second 4-membered ring metallocycle, because it's also a metallocycle, right? It's a 4-membered ring, it's a cyclic structure with a metal in it, is formed when ruthenium adds to the least substituted carbon. Notice how it's bonded to carbon 1, the least substituted carbon. Do you see that? So the first step, it adds to the more substituted carbon so it can become part of your chain. Now that it's part of your chain, it adds to the least substituted carbon. If it added to carbon 2, let me just do this really quickly. You should try to draw out that product. This is an equal sign. I don't want you guys to think this is the double bond. If it adds to carbon 2, ruthenium is going to add to carbon 2 and carbon 1 is going to, it's zigzag. It's going to look as follows. And I know I've stopped drawing it in black. That's because it's really a mess. 2 is now bonded to ruthenium, and 6 is now bonded to carbon 1. But carbon 2 is still bonded to 1, and carbon 6 is still bonded to ruthenium. You've made a bow, right? It's crisscrossed now, which isn't going to happen. That's just not going to happen. A 4-membered ring is already hard enough to make. A crisscross is just almost nearly impossible and not favored. So you always add to the least substituted carbon and you form your 4-membered ring. Now that you've got your 4-membered ring, it collapses again. So the same steps, collapses again, collapses. And once it collapses, notice that you're forming a double bond between 2 and 6, which is exactly the product that you want. That's exactly what you want. Look at what we have written out. Perfect. The problem is that I still need to make my byproduct and I need to regenerate my catalyst. All I've got from that collapse is, if you notice, is my ruthenium with my 2 chlorines, my phosphorus, and my carbon 1 alkene. That's not my catalyst. I need to figure out how to get from here to my catalyst. And so that's what we're going to work on. This step right here. Okay. So I'm going to draw that. If you notice, it's a pretty lengthy catalytic cycle. Okay. I'm going to work this down here. And let me redraw it for you. And so what do I do now? This is carbon one. Well, if you remember, I had a byproduct, styrene. I need to bring that back because that's part of carbon seven. Okay. Again, I complex my ruthenium, um, carbene, and my styrene. It does its pseudo-migratory insertion. Notice that the ruthenium adds to the more substituted carbon. I did my pseudo-migratory insertion. I form my four-membered ring metallocycle. It collapses. So you can see how I'm forming my byproduct, which is the double bond between carbons 1 and 7. Okay. This is the new double bond, and it's starting to look like my ruthenium catalyst. Where the only difference between this is the addition of PCY3. So I have to finish this off by adding the PCY3, the phosphorus ligand. So again, ligand association comes back, and I've regenerated my catalyst. Really clever on how the catalyst is regenerated. Okay. So the rules are always add your ruthenium to the most substituted carbon so that it's part of your chain, and then add it to the least substituted carbon. This reaction should really remind you of the Wittig reaction, okay, where similar to Wittig reaction from second semester OChem. And not only second semester OChem, but I mean, we talked about the Wittig reaction when we were talking about alpha alkylation and total syntheses of a lot of these molecules, right? And I told you, hey, for a Wittig, you need a phosphorus ylide. And you form a four-membered ring. It collapses and it forms an alkene. Plus the byproduct. The difference is that now, excuse me, we're changing the phosphorus to a metal. We're still going through the four-membered ring. It's still collapsing. But now we're using metal chemistry to do a lot of this work. Okay? Again, you must always regenerate the catalyst. Always. There's no ands or buts about that. So don't omit that. Okay? As you're regenerating the catalyst, you will always be forming your byproduct that comes along with the reaction. Okay. So just be careful when you do this catalytic cycle. You not only have to worry about the product, but the byproduct and the catalyst. Please also notice that it's not reductive elimination, oxidative addition, um, beta hydride elimination. The steps have changed completely from what we're used to. Okay. Okay, I'll go ahead and stop this lecture here, and then we'll continue with more examples in the next lecture.